In this video, we're going to go over the back side of the Mathematics of Circular Motion paper. So there were some more difficult problems on this side, so if you had questions or got stuck, hopefully this will help you out. So number 2 says determine the minimum speed at which, and so we're trying to find V here. And part A says the riders on the coaster car feel weightless at the top of a 4-meter loop. So if the riders feel weightless, that means that they're basically in free fall, and the normal force acting on the riders would be 0. And so our gravitational force would be the only force acting on the riders, and that would be equal to our net force. And we know that net force for objects moving in a circle, I'm just going to call it FC, is equal to m times v squared over r. And here, let me put this up here too. So this is equal to our centripetal force too. So we can plug in the 4,900 for the centripetal force. We can plug in the 500 kilograms, which was the mass from the front of the paper. And we can plug in the radius of the loop, and we're going to be able to solve for the speed that they're going. So to solve, we're going to multiply both sides by 4, and that's going to cancel out on the right-hand side. And then we are going to divide by the 500, so we have 4 times 4,900 on one side, divided by 500 equals v squared. And so we can plug that into the calculator, and then whatever number you get, you're going to take the square root of, and your final answer should come out to 6.26 meters per second. For part B, we're going to do a similar thing. It's the gravity that is acting as the net force again. So the weight of this bucket full of water was 19.6 newtons. And so that's going to be our net force. So we're going to plug that in, 19.6. The mass of the bucket with the water was 2 kilograms. The V is what we're trying to solve for. And it says we have a circle with radius of 0.8 meters. And the steps are the same. So we're going to multiply both sides by 0.8. And then we're dividing by 2, and that's all going to equal v squared. And so you plug the 0.8 times 19.6 divided by 2 into the calculator, and then whatever number you get, you take the square root, and that should come out to a v of 2.8 meters per second. Number 3, the coefficient of friction between an 125 kilogram car and the roadway is 0.85. Determine the maximum speed at which the car can maneuver through the curve with a radius of curvature of 25 meters. Begin with a free body diagram. So the car has 3 forces acting on it. As usual, we've got weight acting down, we've got normal force from the road acting up, and then the force that's pointing to the center of the circle, the centripetal or the net force in this case, is going to be our frictional force between the tires and the road. So, like we did in the previous problem, we're solving for speed. We know that the friction is equal to the net force, or the centripetal force. So we're going to plug in friction and set that equal to mv squared over r. And the friction force, we need to actually figure out what that is. So we're going to plug in the friction formula, which is mu times normal force. And in this case, because the car is not accelerating up off of the ground or crashing through the ground, the normal force and the gravitational force have to be equal. So we could also write this left-hand side of the equation as mu times m times g. Okay, and again, we're solving for the v. So since we've left it in variables, you can see that the mass is going to actually cancel out. We want to get the v by itself, so we're going to multiply both sides by r. So we have mu times r times g equals v squared, and so we're going to have to take the square root of that to find just v by itself. So we have v equals mu times r times g. Now, if you're into memorizing, this can be a useful equation to memorize because it's going to hold true for any situation that's like this. When you have a car turning a corner, to find the maximum speed, you can do the square root of mu, the friction coefficient, times the radius times g, which is 9.8. So let's plug in numbers here. So this would be the square root of 0.85 is the mu, r is 25, and then g is 9.8. And if you solve for that in the calculator, you should get a top speed of 14.4 meters per second. Okay, for number 4, it says an airshow pilot makes a vertical loop with a radius of curvature of 84 meters. Determine the force acting upon the 65.2 kilogram body at the bottom of the loop if the airspeed is 62.0 meters per second. Begin with a free body diagram. So if we're looking at a vertical loop, we really only care about the forces that are happening in that plane, in that dimension. So we're going to look at vertical forces. So we've got the weight of the plane acting down, and then we've got the lift force acting up on the plane. But if we're trying to determine the force acting on the pilot, the 65.2 kilogram body, then that upward force is coming from the normal force, the force of the chair on the pilot's butt. So we're just looking at gravitational force and normal force, so nothing too crazy. And we're moving in a circle, and we are at the bottom of the loop. So if this is my circular path, here's my airplane pilot, and then we've got the two forces acting up, or one force acting up, the normal force, and then gravity acting against that. So we can say that the net force equals mass times velocity squared over r. And the net force, we're going to plug in our two forces. We've got normal force acting towards the center of the circle, so I'm going to write that force first. And then I'm subtracting the weight, which is acting against it, and then setting that equal to mv squared over r. Okay, and in this case I'm going to be solving for normal force. So I'm going to add the gravitational force to the other side. We're going to add it to both sides so that it cancels out on the left. And then remember, we can always write out the gravitational force as m times g. So once we get to this point, we have all the numbers that we need. So we've got the mass of 65.2 kilograms. You have the radius of 84 meters. You've got the velocity of 62 meters per second. And then you know that g is equal to 9.8 meters per second squared. So you can go ahead and plug in numbers, and you should end up with a normal force acting on the pilot of 3,623 newtons. The next question says we have a 54-kilogram roller coaster passenger moving so fast over the crest of the hill that she is lifted off her seat and the safety bar exerts a downward force upon her body to keep her in the car. The speed of the car is 24 meters per second and the radius of curvature is 30 meters. Determine the downward force applied by the safety bar. Begin with a free body diagram. So our free body diagram, remember, if you're asked to do this on a test, you should just draw your object as a dot. I've been adding my arrows to the pictures, and you shouldn't be drawing any fancy pictures for your free body diagrams. Remember that, you're just doing dots. So we've got two downward forces acting on the person in the roller coaster. We've got their weight, and we've got the force of the bar. Just call that FB. And both of those arrows should be on the dot. I've been doing this whole thing writing with my fingers, so I apologize for the sloppiness. You should have two downward arrows on that dot. So if we want to solve for the downward force applied by the safety bar, we need to look at the overall situation as we're going over the top of a hill, which is really just part of a circle, right? So we can say that the net force is equal to m times v squared over r. And the net force, we have to define that in terms of these forces we've put in our free body diagram. So both the weight and the force of the bar are pushing on the rider towards the center of the circle. So we're going to write both of those together. We're going to add them up and set them equal to the mv squared over r. And we want to know just the force from the bar, so we're going to isolate that on the left-hand side. So we're going to subtract Fg from both sides. It cancels out on the left, and we're left with Fb equals mv squared over r minus Fg. Again, Fg is equal to m times g, so we can just say F from the bar, Fb equals mv squared over r minus mg. Okay, so again, all of the variables now that we have in the problem, we can apply them at this step. The mass of the roller coaster passenger was 54 kilograms. The speed of that cart and hence the person is 24 meters per second. The radius is 30 meters. And again, remember G is 9.8. So you should be able to plug all of those values in and get a force for the bar of 508 newtons. Okay, so part 6 had 3 parts. We're just going to do the math for one of them, and you can check the answer key to see the math on the others to make sure that you get those correct. But it's the same process every time. So I'm just going to focus on Hill A. It says you have the speed of a 600-kilogram roller coaster car at the top of 3 consecutive hills are shown below. The radii of the hills are shown. Determine the acceleration of and net force and normal force experienced by the car at the top of each hill. Okay, so the first thing it asks us to find is acceleration. Remember that acceleration for an object moving in a circle is equal to v squared over r. So we're going to plug in our v of 6 and our r of 8. So we've got 6 squared, which is 36, divided by 8. And our acceleration comes out to 4.5 meters per second squared. To find the net force, we would do mass times acceleration. So we're going to do 600 times 4.5. And we get a net force of 2,900. Oh, I'm lying. I'm sorry. I'm looking at the wrong thing. 27. Rewrite that. 2,700 newtons. Okay, and then for the coaster car, the forces that make up the net force are an upward normal force from the hill surface and a downward gravitational force. And we need to know the value of the normal force. So we can say, since these two forces make up the net force, we can say gravitational force, which is the force acting towards the center of the circle, we write that first, minus the normal force, which is acting against it, is equal to the net force. So I can plug in a 2700 for the net force. For the weight, I'm doing mass times gravity, so I'm doing 600 times 9.8, and that's still minus Fn. Sorry, I kind of ran out of room there. And so then I would end up with 2700 equals 5,880 minus Fn. And I want to add the Fn to both sides so that it's positive. So then I would have Fn plus 2700 equals 5,880. And then I'm going to subtract the 2700 to get the Fn by itself. So I subtract the 2700 from both sides. And you should get 3,180 newtons. So again, I encourage you to try Hill B and Hill C on your own, and you can check those answers using the answer key that's posted on Google Classroom. I hope that this was helpful for you. If you have other questions, please feel free to come into tutoring. Tutoring for this week is posted on the front board in the top right corner. Have a great day.